Hey everyone, welcome into this motivating example video on partial fraction decomposition. So in this example I'm going to show you, let's just start with our goal here. Our goal is to try to find the antiderivative of this function, and we're going to approach this in a way that maybe is going to be a little crazy from the beginning, but we'll talk it through, and then in the next couple of videos we'll derive a formal method for computing this partial fraction decomposition. So here's the integral. It's the integral of the rational function 2x squared minus 3x plus 7 over, in the denominator, x cubed plus x plus 2 dx, and we want to try to integrate this, or find the antiderivative of this. And it's really not clear what to do. It's not a stare at it. It's not in a form that looks like it would be conducive to a trig substitution. And so what we can do instead is we can notice, and again, this is the part where it's not clear how I'm noticing this, but let's just look at this and make sure that we agree. I'm going to say we can notice that actually this integrand, 2x squared minus 3x plus 7 over x cubed plus x plus 2, this is a rational function, right? This rational function is actually equal to the sum of two simpler rational functions. So 3 over x plus 1 minus x minus 1 over x squared minus x plus 2. Now, we should not just take my word for this, right? We should actually add this up and compute this and make sure that these two are truly equal as rational functions. So how do we add rational functions? Well, these are fractions, right? So we need to make sure that we have common denominator, and that means that we need to actually kind of give ourselves some room and multiply the terms of these by the opposite denominators, right, to make sure we get the common denominator. So I'm going to write this as x squared minus x plus 2 over, I gave myself more room, but still not quite enough, right? So make sure you give yourself enough room to work this out. And then the common denominator on this side is going to have to, it's going to require an x plus 1 down here, right? So we have to multiply top and bottom by x plus 1. And so now I'm just going to carefully multiply all this out. This 3's got to distribute to everything. So this is going to be 3x squared minus 3x plus, that's a 2, it's hard to read my writing, so plus 6, over the denominator is going to be the product of these two. So when you multiply these out, you get x cubed, x times x squared. So these are both going to have the same denominator. We only have to do it once, right? And then we get, that when you go to the next ones, minus x squared plus x squared from these terms, so those cancel. And then it's going to be plus 2x minus 1x, so that's plus x. And then the only one left here is the plus 2, right? And so that's going to be the same denominator for the second one, but we're going to have to multiply the numerator, and this is a minus sign. So there you go. There's almost a horrible mistake due to the fact that I cluttered my writing here. So make sure you do not clutter your writing, okay? That's a minus sign. It would have been very bad if I messed that up. So there's our x cubed plus x plus 2. And now when we multiply the top, this is a difference of squares. And so this is just x squared minus 1. And remember now that we are subtracting these two fractions, right? So when we combine two fractions, we have the common denominator, which is now common. We made it common. And then we subtract the terms. So we have 3x squared minus x squared. That's 2x squared. Minus 3x minus 0, so minus 3x. Plus 6 minus a negative 1. So that's 6 plus 1. So that's 7. And now look, we compare. We've got, by the way, I wrote this down. I claimed that this was an equal sign. That was a question mark, right? Was it really equal? It's not clear, right? So that was our claim. And it turns out, though, that yes, indeed, as long as I did the math correctly, the numerators are the same, the denominators are the same. That means that the fractions are the same, right? Or the sum or difference in this case of the fractions are equal, right? The two functions, as functions, they are equal. So let me rewrite what we've done here, because I really cluttered this up as we went along. So we just saw that our fraction 2x squared minus 3x plus 7 over this x squared plus x plus 2, this is actually equal to a difference, or you could say a sum, because difference is just a sum with a factor of negative 1. But it's equal, I'm going to call it a sum. So it's equal to the sum of 3 over x plus 1 minus x minus 1 over x squared minus x plus 2. All right. If the functions are the same, then their antiderivatives must be the same, right? So in other words, if these functions are equal, they must have equal antiderivatives. And so this is the real crux of the argument for the partial fraction decomposition. You know, when you add two fractions together, you get a somewhat more complicated fraction. It's simpler in the sense that it's a single fraction, but as a fraction goes, as a rational function goes, it's a little more complicated in general. And harder to integrate for sure, right? Harder to notice the integrand. So instead of integrating this function, this rational function, we can integrate this combination, this linear combination of these two functions. All right, and so this is the conclusion here. We're going to compute this integral that we were originally tasked with computing. Make sure your penmanship is good. By instead integrating this function that it is equivalent to, right? So if these things are equal as functions, they have equal antiderivatives. All right, and what makes the right-hand side better? Well, we can distribute, integrals are linear, right? So we can distribute this out and write this as 3 times the integral of 1 over x plus 1 dx minus the integral of x minus 1 over x squared minus x plus 2 dx. And then these two integrals, this one for sure is a stare at it. We know what this one is, right? And if you can't stare at it, that's okay. So this one's you would set your u equal to x plus 1, and then automatically you get your du is equal to 1 dx, so that's all this. And so this is a du over u. I'll write this in steps. So that's a du over u minus, I'll leave this minus sign here. This one's going to be, instead of using u, I'll use a v here. So this one, the v, you will choose the bottom, right? So this is not going to be, did I write this correctly? Yeah, I did. All right, in my mind, this was going to be a simpler one, but it all works out. Yeah, we did this properly. So now we have to be a little more careful with this. So we have to be more careful with it. I'm going to do it anyway. So v anyway here is equal to x squared minus x plus 2. And then the dv, we don't get to choose, right? So dv is going to be 2x minus 1 all times dx. And this time we don't have it. We don't have it. All right, so we're going to need to deal with that one separately. So let's first write down the answer to this one. So this one's going to be 3 times the natural log of u, but u is x plus 1, right? So this part is 3 times the natural log of x plus 1, should be absolute value bars here. All right. And so the question is then, how are we going to deal with this one? So we need to do a couple things. We need to get a 2x here for our dx, because we would really like to make this a log if possible, right? So we're going to do it. We're going to put a 2 here, but it's got to be multiplied by everything. And then, of course, we have to divide it out here, right? And so I am now going to take this entire integral and give myself more room. All right, I'm going to want to come back here to write the answer. So I'm going to come over here and write. So now what we have is negative 1/2 integral. This is now 2x minus 2 over x squared minus x plus 2 dx. This is what we want, right, for our dv. We've got kind of that, but actually there's an extra minus 1 here, right? It's minus 2, it should be a minus 1. So what we can do is we can break this up. We can say this equals negative 1/2 integral 2x minus 1 minus 1. All right, that's just taking the minus 2 and breaking it up. X squared minus x plus 2 dx. And then, of course, we can chop this thing. The whole idea here is we can chop this off right here. And again, integrals are linear, right? So we can break that into 2 integrals. We just have to be cognizant of this term right here the whole time. So this now becomes the integral, negative 1/2 integral 2x minus 1 dx. That's good. That's what we wanted, right? All over x squared minus x plus 2. But then we have this minus 1 and another minus 1/2. So this then becomes plus 1/2 of the integral 1 over x squared minus x plus 2 dx. All right, this first one, we set it up so that this is our negative 1/2 of dv over v. integral of dv over v. Right? That was how we set it up. We rearranged the top so that we got this to be dv over v, just like we wanted, right? So that's going to be a log. And then this one, plus a half of the integral 1 over, this one we should do by trig sub, right? So we need to complete the square on this one. So the bottom here, I'll just write it in a couple steps. X squared minus x, this is going to have to get added a quarter, and then minus a quarter plus 2 dx. And the first portion here is a perfect square. All right, so on the first term we have negative 1/2 natural log of v, we'll come back to that, plus on this one we now have plus a half integral of 1 over x minus a half quantity squared, and then it's going to be plus 3/4, but I'm going to write that as plus root 3 over 2 quantity squared. And that's because I'm now going to do a trig sub on this second portion, right? So this one still has some integral left to be done. So let's see, right? So what are we going to do? For this one, we're going to let there's a plus sign down here. This one can just be done by u sub now that we've got this there. We don't actually have to do a trig sub, right? We just have to do a careful u sub. So let's do 2 more steps. So we could have done a trig sub here. Want to do it by trig sub? That was my first instinct. So let's just do it by trig sub. So let's let x minus a half equal, so there's like the u, it's got to be equal to a times tangent because of this, right? So it's going to be root 3 over 2 times tangent of theta. And then our dx derivative here is going to be equal to root 3 over 2 secant squared theta. All right, and the bottom of this is just going to become secant squared theta, right? Because there's no square root here. So the reason for making this, remember in our table we had a reason. The reason for making this substitution is then that x minus a half squared plus root 3 over 2 quantity squared. This just becomes root 3 over 2 squared, right? So 3/4, so this is then secant squared theta. So this term has to be squared as well, because this whole thing is root 3 over 2 tangent theta squared plus root 3 over 2 squared. So anyway, that's right. So there we go. So now our integral becomes, on this one, just this portion right here, the red portion, this becomes 1/2 integral, this is root 3 over 2 squared secant squared theta, that's in the denominator. All right, that's in the denominator. And in the numerator, we've got our d theta, so that's root 3 over 2 secant squared theta, d theta. And look at this. These cancel. 2 of these cancel, right? Or one of these 2 cancels. And we are left with now, in this case, the root 3 over 2 comes out, and this just becomes 1 over root 3, because everything gets flipped, reciprocal. Integral of 1 d theta, well, that's just 1 over root 3 times theta. But theta we can solve for, right? So we go back over here now. We're almost done, I swear. So we go back over here now, and we see that our tangent theta is equal to, again, multiply by the reciprocal, multiply the 2 through. This could be written as 2x minus 1 over root 3. And so this tells us then that theta is equal to the arctangent of this ratio, 2x minus 1 over root 3. All right, and so that's our answer, right? 1 over root 3 times that. And that's got to go back into here. So now I need to gather everything. I need to gather everything back together. So we need this. Whoops, that was supposed to be a highlighter. We need this. We need this, remembering what our V is. And we need this. Now and remember that minus sign, right? Although I kept that minus sign with the integral, actually. I kept that minus sign with the integral. So we're going to erase the minus sign. All right. So it should have been a plus. Now, it's good that I kind of messed up. I was in my mind when I set up this problem. In my mind I made a mistake. I thought this was going to be a really simple integral right here. It's actually good that it wasn't as simple as I thought, because the point here is not that this is, you know, the easiest thing you've ever done in your life. The point is that we're going to get an answer, right? Because otherwise, I mean, that's the whole goal. You need to get an answer when you do an integral, right? Well, your hope is that you can get an answer to this antiderivative. And we are going to get one now. It took a lot of work and some, probably, hopefully, every time I said something that you needed to think about, you pause the video. Okay, so maybe a little extra time. But here's the answer now. So let's write it out in a couple, let's review, right? So we have our integral of, the integrand was 2x squared minus 3x plus 7 all over, and the denominator is x cubed, should be x cubed plus x plus 2, right? So this is a typo here. X cubed plus x plus 2 dx, and this turns out to be, make sure we get all the parts, so it's 3 times the log of x plus 1, 3 times the log of x plus 1 absolute value, minus 1/2 the log of v, but remember v is this x squared minus x minus 2. All right, so this is minus 1/2 log of x squared minus x plus 2. Let's make sure that was right. That's our v, right? And then finally, we have, this became a plus as part of the computation, right? We had a minus 1 we had to take out, so this is, all the signs are correct. This is the hardest part now, doing the bookkeeping. So we have to finally add in plus 1 over root 3 times theta, but theta is this arctan, right? So this is 1 over root 3 times the arctangent of 2x minus 1 over root 3, and then once you're done, you always get a plus c. All right, so this is the antiderivative that we desired. It took a lot of work, but we got there. That's the whole point. We got there. So in the process, what did we do? We used our knowledge of trig subs right here to get this last integral, right? So that's just the last portion. Before that, we used our u subs to get, or I called this a v sub, but u or v subs to get our natural log terms, right? But the key here that is different and new is that we noticed at this point that we could break up our rational function into a sum of two quote-unquote simpler rational functions. Now, it still took us a lot of work after we did that, but that was a step that allowed us to do everything that came next. Okay, and that's what's called the partial fraction decomposition. So there's our motivating example with a little bit more motivation than I originally intended, but this is a good one. And in the next video, I'm going to try to lay out a general algorithm or method for performing the partial fraction decomposition from scratch. Because the real question here is, how did I know that these were the right fractions, right? How did I know that these two fractions were the right fractions? And so I'll try to answer that question, at least partially, in the next video.